There you go. I can see
Excellent.
that live on YouTube.
Thanks, Sue.
Are we good to go?
I am just confirming.
I've got the YouTube live feed on my computer.
Yeah, we're good.
All right.
Thanks so much.
So you've got control.
Awesome.
So Paula, you
Thank
two
you.
look like you're in Italy or something. It's the Venice canals behind you, or it's the French bridges in Paris, huh?
I think I was told it was Singapore.
Oh.
I want to say hello to Joan because Joan is joining us from the Blue Water Astronomy Club up north tonight. And I have to thank Joan because I went to one of her public outreach nights and we spent a lot of time together looking at the night sky, and she told me, well, you're hooked. And she was right.
Yeah, that was
welcome tonight.
Okay, that was quite a while ago. How long ago was that?
Oh my goodness.
Because I haven't done outreach for quite a while.
You know what? Maybe 10 years, 11 years. But I remember standing out beside the Outdoor Education Center on the top of the hill. And I was like, I could have done that all night. So
glad to have met you.
It was before Fox was built.
Yes, it was before Fox was built.
Yeah.
Hey, everybody.
Hi, Melissa.
Hello. Hey, so there are some people who may be newcomers to Zoom. Forgive me if this is old news to some or all of you, but if you're just seeing one big speaker in the middle and then a thin strip across the top of 4 or 5 people, there's a different way to view your screen. In the upper right-hand corner is a button that looks like that. And if you click on it and select Gallery View, you'll be able to see a lot more videos simultaneously. You'll lose the Zoom view, so you won't be able to count eyebrow hairs or nose hairs of the speaker, but you can probably do without that.
I'm in gallery view by default.
Yeah, that's good that you are. Some people aren't familiar with gallery view.
Lorraine.
Hi, everybody.
Hi, Lorraine.
Hello.
Hey, Mario, how are you, buddy?
Good. How are you doing, Jimmy?
Good. I see Jim. Hi, Jim Couch. You don't have your audio on, Jim, but that's okay.
Don.
I see Joanne has joined us.
And I do want to say hello. There are some more people joining us from the Blue Water Astronomy Club up north. So welcome to the HAA general meeting tonight. I just want to let everybody know that we are recording and streaming live to YouTube at this point in time.
And Sue, Matthew can't be here with us tonight, unfortunately, as you know, and some of the others of you know. Matthew's dealing with a family crisis at the moment. So without this month's edition of The Sky This Month, I think we can probably forego the intermission. And then that will allow us afterwards a little chit chat time, perhaps, for those that would like.
Yep.
We will be ready nice and early.
So fantastic. That's great. Thank you very much. Hi, Maya. How are you?
Good. How are you?
Very good. Thank you.
Yeah.
So, hey, and there's Brian. Brian, that's quite a mop of hair you got going on there. I haven't seen you for a while.
Growing it out.
Nice. Good for you.
It's usually at this point that I hear my father say, "Get a haircut, you bum."
Got mine done today, but you never know. It's...
think Jeffrey's actually intrigued. Let's see where this goes.
Oh my, look at the head.
Talking to a friend here.
My goodness.
For those that would like.
Yeah. We will be ready.
There we go.
You get.
What are we doing here?
How are we doing?
So John,
Yes,
are you, I guess you must have got off work early today.
I made arrangements to be here tonight.
Good. Are you doing 5 days or more than 5 days a week?
It varies.
Okay.
It varies. So,
Okay.
John, it is 7:30, so I'm just going to remind everyone again that
Anybody
we
hear me?
are recording, and yes,
Hello?
Michael, we can hear you. Can you hear us?
I wonder if Mike turned his speakers on.
I asked him, he says he did.
Okay.
I'm just going to try one more time. Michael, can you hear me?
Anyone hear me? Hello?
Yes,
There he is.
Michael, we can hear you just fine.
I can hear you, Mike.
My camera hasn't come on.
That's because your camera
did
is
the
turned
last
off
time.
right now, but that's okay because we're going to start the meeting and I'm going to ask everybody to turn off their cameras and their microphones anyway. So you can just leave your camera off for now and just turn off your mic,
Hey, they can
okay?
leave their cameras on. I need a live audience. Otherwise, I'm just talking to my screen. Leave your cameras on unless you're nodding off or
Well,
taking care of some personal business.
We sometimes have issues with bandwidth.
Really?
So if
Hello?
people have, our protocol has been to have cameras
You guys
off.
know what's best.
So if people do keep their, it's a larger group, so we do cameras off. That's kind of been our protocol, but we're still all
wait a
here.
minute.
So don't worry, we're not going anywhere. I don't think.
Okay. I'm in.
All right,
I'm
Michael, you okay?
in. Can you
All
hear
right.
me?
Mike,
Yep. We can hear you and we can see
Okay.
you.
Yeah.
Yeah, I'm in. I can see everything. Yeah.
Okay.
Can you hear us, Michael?
Say again?
Can you hear us?
Yep.
Wonderful.
So Mike, you
wonderful,
gotta
that's great.
mute
Good.
your
Glad-
microphone now, Mike, so we
Glad
can have the
everything
meeting.
is going
Oh,
well,
yeah, I know.
Michael. Now, Michael, now we need you to mute your microphone so that we can turn our attention to our speaker this evening.
Okay.
And while Mike is doing that, just one last reminder, because a couple of people just came in, we are recording and we are streaming live to YouTube. So John, it is all yours.
Thank you very much, Sue, for that reminder. Welcome to everyone to the March meeting of the Hamilton Amateur Astronomers. It's good to see you all, or at least see a virtual representation of you. For those that don't know, and you all do, but for those that don't know, of course, I'm John Govro, and I'm the chair of the Hamilton Amateur Astronomers, or in this case, I'm a virtual representation of John. So it's great to have everybody here. It's wonderful to have some nice weather. I'm sure, like me, many of you are itching to get outside and get out under the sky without having to worry about the telescope lens frosting over. And we have some good practical oriented stuff to talk about tonight that I'm very much looking forward to. We normally, of course, we have a two-part program. Tonight, we've put all of our eggs in one basket, and it's a terrific basket at that. So we have with us here Tom Field, and Tom is the founder of Field Tested Systems. Tom, a very clever name, I must say. Well done. where he has introduced countless numbers of people to real-time spectroscopy. They do hardware, they do software. It's very impressive. For the last 10 years, Tom has been a contributing editor to Sky and Telescope magazine. I don't know if the camera will go this close, but there you go, right there. There's Tom right there. You know, right in between. Tom, you're right in between Alan Dyer, a good Canadian there, Alan Dyer and Tony Flanders. So you're an excellent company. Well done indeed. So tonight, he's going to introduce you to the amazing field of astronomical spectroscopy. I know there are a couple of you in the audience that are familiar with this, that have tried your hand at it even. And for those that haven't, then I know you are going to be inspired, okay, by this to find out what this is all about. It is entirely worthwhile. So I know that you would join me in giving Tom Field a very warm welcome. Tom, welcome to Hamilton, Ontario, Canada. The floor is all yours.
Thanks, John. What a great introduction. I've never had anybody hold that masthead thing up there. And I'll tell you, I'm such a knuckle dragger and I'm just such an amateur that I really get a kick out of having my name on the masthead. I haven't written anything. Shh, don't tell anybody. I haven't written anything in a half a decade or more. In fact, I just got a letter from the editor-in-chief, we all did, saying, in order to keep our masthead current, you have to submit a feature-length article once a year. So I'm going, now what? But thanks for the introduction, John. And thanks, as I said, you and I have been talking since November of scheduling this. And it's behind the scenes, a lot of what you all do in the administration of a club. And people should know that it's not just a matter of a phone call or two. There's emails and schedules and all that stuff, and as well as the newsletter stuff. And Sue, thank you so much also for helping bring the meeting to order. I'm going to talk for about 50 minutes. I'm sorry I won't get to see many of you faces as I talk. And that's okay. Hello, if they're still watching. I think it's Brian and Maya, the Whitman family. Thanks for joining us. I hope you'll stick around until I get too boring, which can happen pretty quickly for almost anybody. But I'll try and keep it lively for my talk. And then when we're done, there'll be Q&A. Also, my email address I'll share at the end, the website as a contact form, lots of ways for you to get in touch with me. So with that, I do want to share my screen. So let's get started if I can find it there. Let's see, we'll go like that. And then give me just a moment, because sometimes Microsoft Windows and PowerPoint decide to make trouble. So let me just have it show the slideshow there. And there it is, one more step for all of you. And off we go. Great. Just get a couple more things arranged. One thing I don't like about Microsoft, I'm in Seattle, so I get a little bit more leeway in dissing them, is every single time I go in and out of PowerPoint, I have to remember to tell it not only to hide my, there we go, I have to tell it to make my cursor remain visible permanently. Great. So good evening, everybody, and thanks so much for the invitation tonight. I always like to put a slide up with the club's logo, just so people know this isn't a totally canned presentation. And one thing that can be problematic about that is that, as some of you know, there's more than one Hamilton Astronomical Society. And so I almost stuck with this one before I read the fine print and realized that it wasn't the right club. So I'm glad for that. There we go. I've just grabbed what I need. So how have we managed to discover so much about the universe when we've barely stepped out the door, really? So images, we can see, two-dimensional views of the universe, and we've been doing that for, 150 years or more. We can get fleeting glimpses of a third dimension, right, during eclipses when one object passes between us and the other. And if we wait, a fourth dimension, time, reveals itself. You can see up, especially up there in the upper right-hand corner, if you have trouble spotting it, You can see some stars going on and off. These are some periodic variables that change in intensity and we use to measure distances. And if we spread the colors out, we get this. Oh, this slide I brought up on the screen just to show you, and I can't bring it up right now, but I brought the Microsoft's Bing Maps up to see exactly where Hamilton was. You're probably the closest to where this photograph was taken of any club I've ever spoken to. This was taken in Lake George, New York, last spring. So if you spread the colors out like this, I spent many a summer camping up there, what you get is something that looks like that. Gorgeous rainbow. And notice there are a lot of gaps. And we're going to talk a lot about why those gaps happen and what they can tell us about the stars. Now, the next slide used to be a bulleted list of everything I was going to talk about because I decided let's just tell them out in the open, up front, here's what you're in for. And I realized it was wasting time. Nobody wants to hear all that preview. But I thought I'd try this, which is a ding moment. When I come to one of those critical bullet points that it's something that I wanted to make sure that I communicated, I'll call it a ding moment, and that way I'll get have my cake and eat it too. These spectra with these gaps reveal our star's barcode, and we can identify different chemicals and other physical properties. Now, again, I won't read these bullets here, but these are the kinds of things that we can tell from a spectrum. They say about 80% of the astronomical research that gets done is done with spectroscopy. So listen, a lot of you I know probably aren't imagers. You may not be interested in doing what I'm going to talk about tonight. Maybe you're even an armchair astronomer and you don't do any hands-on observing, except maybe looking under the stars bare-eyed or with binoculars. That's okay. Because so much spectroscopy is used to learn what we've learned about the stars. Even understanding what I'm talking about without plans to do it yourself will deepen your understanding of the articles that you read and that we all read in the magazines, even the magazines on whose mastheads I am, but for which I haven't written an article in half a decade at least. So I'm a one-trick pony. It's a great trick, but it's just one. So, a little bit of history here just to get everybody more or less to the same level. Of course, Sir Isaac Newton split light using a prism and was able to determine that the component colors were all in white light and they were separated out as if by the prism. You can also bounce light off a finely grooved surface or even through a finely grooved surface to create a rainbow of the component colors. Bunsen, many of us have heard of, invented the Bunsen burner to burn elements and then put that light through a prism and then over here study the resulting spectrum. He was a pyromaniac. He burnt everything he could get his hands on. And the great thing is he kept a catalog of his results, and that really served us and to this day does, as we'll see. This fellow over here, Kirchhoff, was a colleague, friend, and we're not going to get into a lot of detail about Kirchhoff, except, and that's not at all what I wanted to see there. So there we go. And it wasn't Bing Maps, it was Google Maps. I want to start one thing here, if you don't mind. There we go. That's my pointer. So we'll come back here and go back there. There we go. So there are two different types of spectra that we can get. One looks like this, and it's just, as you can see, it's a rainbow with gaps. And this one down here is more or less a dark background with just lines. Now, what you get is what Kirchhoff talked about. We won't, but it has to do with the temperature of the gas through which the starlight goes when it's leaving the star and so forth. So, but you can see that each element has its own fingerprint. And they're different, right? Just like fingerprints on humans are different. So this bright line right here on hydrogen doesn't exist in helium. And in fact, hydrogen is so common in the universe that we've given the lines that hydrogen produce in a spectrum the name Balmer lines. And we've actually named the Balmer lines with these Greek letters. So for example, this beta line, that's what? That's aqua, baby blue, robin egg blue, let's call it. And we're going to see a lot of these lines as we go on tonight. So very briefly, this is a periodic table I created a few years ago. We sell it mostly to teachers and the amateurs who are particularly excited about spectroscopy. It's likely there's an amateur radio operator or two in the audience. They tend to run in the same crowd. I almost said, we sell this to the hams who are more interested in this kind of thing. I don't think that would have gone very far. But I wanted to show you here. Here's that hydrogen. So if you were to burn hydrogen, you would see these lines. There's that robin egg blue hydrogen beta. And look how different the lines are in helium. So for example, if you went to a flower shop, oh yeah, I was just trying to remember, had Valentine's Day gone by? Yeah, it has, thank goodness. I didn't miss it this year. If you went to a flower shop and you bought, one of those balloons they inflate with helium, and then somehow you safely burnt that helium and looked at it through a prism, these are the lines that you would see. Very different than hydrogen. So we don't have to burn things these days, thank goodness. Over here on the side, you can see I've got, including a very messy desk, but you can see here is a gas tube. And it's it's just it's sort of like a fluorescent lamp. This is a helium gas tube, and so we can just use those in the classroom, for example, or in the lab. And in fact, some years ago, I created this camera here. You can see it on the screen as well as in my video. This is just a little camera that educators use for the classroom. It's been really popular. So far, everybody I've talked about have been what? Old white men. Let's look at some counter examples, of which there are numerous. So Annie Jump Cannon and her team of women, they were called computers about 120 or so years ago. They were prohibited from accessing the telescopes at Harvard. So what they ended up working on was they studied the glass photographic plates of these spectra, of this starlight that was split with a prism. And that's easy for me to say. And they were really good at it. They processed tons of information, like hundreds of thousands of spectra. Little side story, and I'll date myself a little bit with this. Yesterday, I was at my hearing aid doctor. And we were talking, and I was asking him about all the online data, because it was my sleep doctor. It's been a busy week or two for doctors now that we're vaccinated down here. And I was saying to him, my CPAP machine, my sleep air machine, it uploads my sleep data every night. And he told me he himself have prescribed in his career 30 or 40,000 CPAP machines. I said to him, think about the amount of data, huge amounts of data, and what they could do if they studied it with machine intelligence. And he said that as smart as machine intelligence is, actually, of course, it gives us amazing stuff, including some of the protein folding that has gone into some of the mRNA vaccines and self-driving cars. But he said there's still, even to this day, his opinion, it takes a person looking at a lot of data to start to see patterns that were unexpected. You didn't even know to go fishing for them. And I told him about these women. And in my talks, normally I talk about the fact that it was only after they had seen hundreds of thousands of spectra that they began to sense and appreciate and come up with patterns that allowed them to create a cataloging system for star types that worked, unlike all the previous ones invented by men. So Priyamvada Nataraja, she's at Yale and she studies hyperactive black holes. Very cool stuff. Nancy Grace Roman was the first astronomer at NASA. She got her PhD in the late 1940s. I imagine she was the only woman in her graduating class, even as an undergraduate. She was a big proponent of the Hubble Space Telescope, which you can see there, and helped make it happen. Elisa Quintana, she studies exoplanets and has discovered an exoplanet that's circling a red giant right at the proper distance where water would be liquid and might support life. And finally, Jedediah Eisler, she's at Yale, and she studies gravitational lensing and black holes. By the way, I was just reading on Twitter, I happened to stumble across Priyamvada Nataraja, And she was talking about how some predictions that she made theoretically 25 years ago when she was a PhD candidate were finally borne out in some observations in the last year or two. Isn't that amazing that you can wait that long for some of your thinking? Of course, Einstein waited a long time. I don't think he doubted what he was saying was the case. And what he has said has also, of course, been borne out by many, many examples. So there are lots of women in the field. We've made some progress in opening the doors for them. It's amazing to me, and I'm not going to get on a soapbox anymore tonight, except to say I was thinking about it today, and have as many of you over the years, that fully 50% of the talent and the people who could be contributing to the betterment of humanity have not been given opportunities. We've just been squandering so much talent. Anyway, enough of that, although it's an important topic. What I'm going to talk about tonight is this little grating. Now, this is what definitely a ding moment, because this grading costs about $195. So one of the misperceptions I aim to eliminate in this very slide is, oh, spectroscopy is expensive. Not so. Really inexpensive. And the other thing is, it doesn't require a lot. Another ding. I should just hit this. This is often considered hollow by people, especially my wife. The other problem is that I think a lot of us thought that, well, it's just too hard to do. And again, at the end of this talk, I hope you'll share with me an understanding that it really is surprisingly easy. There's lots of ways to mount a grating. For example, here we've just threaded it on to the lens cap threads with this little adapter that we sell of a DSLR. Here is an example of a Fitz camera. It could be cooled or uncooled, color, mono. Down in the lower right-hand corner here, you can see this is you can see in my video there, this is just one of those ZWO video cameras. I prefer color for reasons I'll show you as we go forward, because I do more outreach and education. But for science, you want to do more mono. Either one will work though. And this is just an example of a filter wheel in which you can mount this star analyzer grating. So you can piggyback a DSLR on your telescope if you want to multitask in your imaging. Okay, so enough about a history, theory, equipment. We're done with all that. What can we actually do? So if we take the light of the star and we put it through this 1¼ inch star analyzer grating, it splits the light just like a prism into a rainbow. And this is what we would see in our image on our sensor. Let's look at one of my favorite examples. These are all different images captured at different times by Torsten Hansen. Look at the top there. He was using just a modest 8-inch Newtonian and an imaging source camera, which is, more or less an earlier generation technology than what we can get with these, $200-300 ZWO video cameras. Some of you probably use them today. And, earlier, one of the bullets I showed you talked about how we can tell star temperature by looking at the spectrum. You can see these stars, once I point it out, you'll see, are in temperature order. Here are the hot type B stars. Here's the cool type M and K. So these are in the Obia G KM order. And look at the differences in spectra when you see them split out by temperature. I'm going to show two quick examples on this screen. One is down here. Well, that's not a line. That's like a forest, right? It's called a band. And it just really occurs on these type M stars, these very cool stars. So what professionals tell us is that on a relatively cool star, some complex molecules can survive. And instead of just a single line, like some of these other lines up here, these complex molecules, where'd my mouse go? There it is. These complex molecules create a forest. Now, the second example I wanted to show you is this one that's down this here. Notice that, even though blue is a bad color to be using here, isn't it? Notice that here on this type A star, that's like Vega, for example, the line is very dark and wide. But on these hotter stars, not so much, nor on these cooler stars down here. So this is that robin egg blue, that hydrogen beta line. Now, why would they be different widths and strengths by temperature? Well, just a quick comment about how these gaps get created on the surface of the star or anywhere we have a spectrum. So you may recall the Bohr model of the atom has electrons going around in circles. Just really quickly here. those orbits are numbered. And when an electron jumps between shells, like from shell 2 to shell 4, light is absorbed. It's like, I think of it as like to pull an electron out takes energy. And so that creates a gap. And different jumps create different color gaps. So this 2 to 4 is this hydrogen, robin egg blue gap, right? So that's really all. Oh, so the deal is, before moving on to the next slide, got ahead of myself there, is these super hot stars, these type B stars, they're so hot that when the electrons get pumped up, they go right past 4 to 5 or even beyond. So they don't make that 2 to 4 transition. So you don't get as many electrons producing gaps. And on these down here, these cooler stars, they're so cool that when the electrons get heated and pumped up, they don't even get up to 4, some of them. They might get up to 3. So there aren't as strong lines here. So now, again, some of you may have seen this earlier. My wife insists that I need to dress for success. And, this is somehow, I don't think this is what she meant. In fact, there's no somehow about it. She's quite clear this is what she meant. But, you can see there that there's the hydrogen alpha line down and then that red region there. And some of you, like me, over the last, say, 12, 13 long months may have experienced the same thing that I'm about to describe here. And that is down at the base. And we're all about color in spectroscopy, right? Down at the base, it's sort of grayish down there. In my salon, they're not picking up. They don't have appointments. So a lot of us have suffered. I know some of you or your spouses have been through this year. But dressing for success is important, I'd say. However, see that crosshair right there? You may be able to see, I'm not playing there. I think you can probably see a little bit of a gap. That may be my averted imagination, but that's in the robin egg blue. But suppose I got time on the Hubble Space Telescope and I captured data and I submitted an article and I said, yeah, in the robin egg blue, we saw a little dimming in the spectrum. It's not going to get published, right? So to do science, we need to be quantitative. And for that, we create an intensity graph like this. So this axis here is brightness or intensity. So the sum of the starlight goes right through the grating, right? It doesn't get bent into this rainbow. And so the star here is bright and narrow. So this is a really tall peak, but not very wide. Whereas this thing over here, right, is pretty dim out here in the wings and brighter in the middle. So this in intensity is dim, brighter, 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 dimmer, 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 dimmer. But check this out. That little dimming I pointed out qualitatively there is really clear in that dip. So now, because we have a dip at a known spot on the graph, now we can do science. We can look at how wide it is, where does it fall, how does it compare to other stars or this star on other nights. Now, it's a stupid pun. It's the first time I've used it, probably the last. Now we're cooking with gas, right? So how do we get that graph? Well, so my story is in 2009, I was not much of an imager. I'd done a tiny bit of imaging, but I wanted to do some science. So I got a grating like this star analyzer grating. I went outside, literally right outside the window. This is Pike Place Market, about 3 miles away in that direction. And it was a Saturday night in August. I set my C8 up. I had literally, I have it here somewhere, a Logitech webcam. I took the barrel off an eyepiece and I duct taped it literally to the webcam and I screwed the grating into it like any filter cell. I came in at midnight. I had some video. In fact, this is a frame literally from that video. And my blue jeans, the knees were grass stained because, it's Vega in August. What do you expect, right? And Sunday morning, I wanted to create this graph. I downloaded the freeware that was out there. And about 2 hours later, I quit. I gave up. I was so frustrated. It was shareware. It was half in English, half French. It's really frustrating, not only when a program crashes, that's the injury, but when the error message that pops up is in French, that's the insult. So I said to my wife, I'm supposed to be having fun. This is a hobby. But I really wanted to do spectroscopy. But I didn't want to be frustrated. I put the grading away. I put it in the drawer. Over the next couple of weeks, I kept thinking about it. And I said, look, next weekend, I'm going to just write a program. I've been writing software literally since the 1960s. I will write a program that will take this image and create this intensity graph. And Sunday morning, I was done. And now 10 or 15,000 hours later, the software is almost finished. Again, my wife, bless her soul, at heart too, she keeps saying, would you finish the software so we can have dinner at a decent hour consistently? It's done, really. I'm joking. But this is definitely a ding moment, because I think most of us, when we contemplate learning a new piece of software, I know I do, there's this heavy sigh, right? Like, oh no, another learning curve to climb. But I know better than to give you a software demo. It's after dinner there. I know, especially if you had your video on, I'd start seeing the tops of heads and hearing foreheads clunk on their mics. So, but I do want to spend about 2 minutes, less than a dozen clicks. And because I want you to see how easy this is. So there's the software, and this is the image. It could be a FITS image that popped in automatically after you captured it with a static FITS camera. It could be a video image like mine here. This is a freeze frame from a video I shot that first night. There's the star, and once the starlight is split with the grating, there's the spectrum. Literally, I mean, that's how easy it is. And you can see there's a gap there. There's some gaps there. So all you do is bracket in that spectrum with this sampling box, and you get that intensity graph. That peak there is from the star. And this data here, dim in the wings, is this data dim in the wings and bright in the peak. And for example, that dip right there is that dip right there. What a terrible graphic. There we go, that one. So big deal, right? So what? They're dips. I felt like the dip after I did this, because then it's a matter of, so what? They're dips. But remember when I was talking about Bunsen, I said he was a pyromaniac. He burnt everything and he kept a great catalog. Well, the great grand catalog is still used today by professionals, by amateurs, and a piece of it's built into the software here. So I can come to the software and say, show me where, on this graph, show me where I would see dips if there was hydrogen involved. And now we can see there's a dip there. There's one there in that robin egg blue. There's one there. Wow. So we are actually with a C8, first time out, urban Seattle, knuckle dragging programmer who is not an amateur, was able to detect the hydrogen on a star. That's definitely a ding moment. So the other sort of cool thing I wanted to show you real briefly, and then we'll move on, is this is actually a piece. Let me turn that off, and I'm going to turn off that color fill, and I'm actually going to start the playback of this video from that first night I went out. Now the image here is jumping around, so our data is jumping around. And you can see dips coming and going. Like there's one there. You can sort of see sometimes it's there, sometimes it's not as clear, right? Now, one of the things that a lot of us are familiar with is stacking images, when you add images together to eliminate random noise. And I'm going to do that in real time here at 2 frames per second. So last thing I'll show you, turn on averaging. Now watch over just 5 or 10 seconds how that average stack stabilizes. Now it's relatively symmetrical and smooth. That's what stacking does. Isn't that cool? So I'd like you, as we leave the screen, to remember this view here. In your mind's eye, just sort of set it aside. And that is dips. Excuse me. And going through those dips are reference lines for hydrogen. Excuse me again. A little bit too much yelling. So we'll calm it down here a little bit. Let's go back to our PowerPoint show. Somewhere here. There we go. So here's something you can do at a star party. And this is a ding moment. And the reason I wanted to point this out is, you know, it's great showing the showpieces that we do at our star parties. They're wonderful, Saturn, the moon, and so forth, M13. But if you add spectroscopy, not only do you get that live color view that I showed you previously in my software, but you get to talk a little bit of science. You don't have to know a lot of science. I mean, really, again, a dingable moment is that you don't have to have an astrophysics degree or be a scientist. You know, with a little bit of reading, enough comes together that you're able to talk about this well with citizens. And it can enhance your outreach. The other great thing I wanted to show you here, as well as you saw an example in my image a few minutes ago of Vega that was, and that is you can do this in the city, even in Hamilton, even with your light bubble, because unlike visual imaging, we're not all concerned about fine gradations and the aesthetics and color balance. We're just looking for freaking dips. And that's relatively easy to do, even in a light polluted environment. So this is a good tool that you can add to your outreach efforts. And at the end of the show, during the Q&A, if we have time and I remember, we can also look at something spectroscopically that you can do during the day on the sun to augment your outreach during the day. So here's a view with a wide field DSLR. There's 3 stars there. There's some gaps and there's spectra. Here's a star here. Notice those lumps. It's not the technical term, but we've saturated the pixels on this emission object. Let's look at a Wolf-Rayet star. Now, I have a confession to make. When Janet Simpson sent me this about 8, 9 years ago, I couldn't remember what a Wolf-Rayet star was. People had, you know, over the years, others and I had talked about them and read about them. But the deal is that especially as we get older, things go in one ear and out the other, right? So, but what I found, this is definitely a dingable moment, is when you have the data in your hands, especially if it's your data, it's a very different experience. You have an emotional commitment, you have an interest, you end up sort of playing with the data, going out and reading little pieces here and there, and you have a conceptual framework to start hanging things so you remember them. Wolf-Rayet stars, Wikipedia being our friend, told me that they're late stage stars, they're massive, they're very hot, enormous stellar winds. Some of the outer shell has been dissipated and we're looking down into the star. It's headed probably to being a supernova. Let's take a look at this emission spectrum just to point out these bright spots here show up as peaks. Carbon, carbon, carbon. Why would we be seeing carbon if stars are made of hydrogen? Well, remember, stars fuse their way through different elements, the sequence of elements, and part of that process, one of the steps is carbon is a byproduct. That's what we're seeing here. Let's look at another emissions object, one of our favorites, the beloved Ring Nebula. There's the spectrum, and you can see just 2 lines, right? As if, well, who else but somebody who's in science would say those are lines, right? Hydrogen alpha and this oxygen, that Roman numeral 3 means that it's what's called ionized. It just means some of the electrons have been pulled out because it's so hot. So most extended objects, rather than point sources, are really boring in a grating like this. This is an exception. I'll show you some examples in a moment of spectra of extended objects that aren't boring. But in fact, here it is. If you, again, invest in a 10-fold more expensive device, then you can get spectra of, you know, the sun and, you know, other objects much more easily that are extended objects. The challenge is now you're guiding and acquiring your target through a 50 or 20 micron slit. So you've got to have really good control, good mount and so forth. Almost nobody starts with a slit spectrometer. But let's look at another emission object, the Orion Nebula. Again, we can see a nice, really narrow, even though it's a wide, broad object, hydrogen alpha, there's that ionized oxygen. What's interesting is, right, this is an early stage, right, birthplace of stars. And this over here, the Ring Nebula, was the end stage of a star life. Both have this hydrogen and oxygen. So I'm going to stop screen sharing for a second because I want to ask all of you, if you're interested, I won't call on anybody, and I can handle it if nobody steps up, to share the first time that you saw the Orion Nebula, M42. Where were you? What was the equipment? What was your experience? Any takers? Bueller? Anyone? Anyone? It's that line just there that I said that I like to have video showing because I like the smile that I get with the Bueller reference from some people. Go ahead. Anybody want to share?
Well, I'm smiling. The Bueller reference made me smile. Absolutely. I got it. I know some of the younger folk listening might not get it, but I totally got it. Absolutely. Good. So, and I can remember the first time I saw the Orion Nebula, and I hadn't joined a club yet. I was a teenager. I had saved my pennies. I got my first telescope, and I was exploring the sky from the backyard on my own, without people to guide me and those first views through a very small telescope under a very light polluted backyard were still magic, still absolutely magic. And I've had many much better views since, but I can still see it in my mind's eye. Just lovely.
John, that is a wonderful description. You have a future in show business. You can join me up here on the stage next time. Very nice. Thank you so much for sharing that. And that's a great story. And I imagine many of you have a similar story to tell about your first experience observing M42. So let me share my screen again. And, my first experience, and it wasn't exactly what I was looking for, John. What I was looking for was something similar to my story here. And that is early 1990s, wanted to see Shoemaker Levy 9, had never used a telescope. In Denver, I went out to the first quarter star party in downtown Denver. It's fun when you can remember back before you knew something. And in this case, I had never looked through a telescope or even seen a telescope in person. I got out of my car. I walked up on the little berm next to the observing field at the Chamberlain Observatory at the University of Colorado. And what I saw, those cannons at the circus that they shoot people out of? I saw half a dozen of those out on the field. I didn't know any better. Of course, they were Dobbs. What would I know? So I walked down on the field. There was somebody like many of you or me running the telescope, talking about this M42 that we were going to look at. I was all excited. I got up to the eyepiece. And unlike John, I didn't have the insight or imagination or knowledge to know what I was looking at. All I saw was a mono smudge. It was like, so? But I'll tell you, here's the deal. Like John, I still go back and look at M42, and I bet many of you do too, even if those initial experiences were disappointing. Now, why? If it's a smudge, well, of course, we've got better telescopes. We're in dark skies. And also, we're much better at averted vision now, right? We know how to look at things with the best part of our eyes. But all kidding aside, I think the reason that we all go back and look, even at a smudge, if that's what it is, and get a thrill out of it, is because we understand what we're looking at. The point is that when we bring our knowledge to the eyepiece, we have a much richer experience. And that's what spectroscopy has done for me. Listen, like I said, I'm a one-trick pony. Or another analogy, I'm like a really broad river that's really shallow. That's okay. There's no quiz. There's no final exam. You learn what you need to know to enjoy yourself. And I found that with spectroscopy, as I said, when you have the data in hand, you do a little more digging. So let's move on to another. We're going to move through some examples pretty quickly here. This is also by that guy, Torsten Hansen, with that 8-inch and a video camera. You can see here is the spectrum of Uranus and Neptune. And down here, you can see the deep dip for these. Oh, those are bands, right? What did we hear about bands earlier? That a band is on a cool object and it's a complex molecule producing that. Well, Uranus and Neptune are plenty cool, especially compared to stars. But what kind of molecule would we see on them? Well, we're seeing the absorption bands of the methane on those planets with a backyard telescope and a video camera. I think, again, that most of us aren't aware until we hear a talk like this that this kind of thing is even possible. So in 1881, Henry Draper, that's the Draper catalog guy, observed the spectrum of a comet, and the New York Times thought it was important enough to report on. Now, look, if Hank can do it, so can we. Here on the lower left, you can see that little string of gems. That's Comet Ison. And on the right, you can see the peaks. Those are called the swan bands. This was captured by Vikram Agnihotri. He lives in Rajasthan, India. He's a nuclear power plant engineer. And in 2013, when he captured this with just a DSLR and a refractor, a small refractor, he was a beginner back then. Now he's really, honestly, he's better at, it doesn't take much, but he's really far beyond what I know or can do. And, or when he bought the software, I thought I'd be really nice. Poor India, they don't have a very wealthy populace. That was my ignorance. But I gave him a discount on the software. Now he's buying, Paramount mounts and, 13-inch, 14-inch refractors. And I'm going, wait a second, no more discounts for you, buddy. He's a good friend. And what teacher doesn't like to see their student go beyond them? And he certainly has done that. Here's a more contemporary example of NEOWISE. You can see there's the sodium lines on it. Now, this slide, anybody who uses a C-clamp as part of their setup, that's my kind of guy. Except in my case, if this was my setup, I would have cranked that C-clamp on that video camera housing so much it would have collapsed. I break everything. That's why I love software. Control-Z, edit, undo is my savior. I wish sometimes we had such a thing in life. Wouldn't that be nice? But fortunately, Robin Leadbeater didn't break his camera here. He put a star analyzer, and he's the designer of the star analyzer, and a real expert, a huge contributor to our community and knowledge. He put a star analyzer on a video camera, and he observed the Perseids. And he got this spectrum. Now that there is the actual meteor, and this is the monospectrum. And so just to orient you, that gap right there is that dip. And you see, he observed all sorts of elements here. Look, this is like a niche in a niche, right? But whatever floats your boat. He does lots of other things besides this, but this is something people get into. So we won't get into much detail on the sun. We heard a lot about it over the last few years, and we'll again in the next few, except to point out that in 1868, these two researchers saw that yellow line at about 5,800. They went to Bunsen's catalog from 10 years earlier. They went through it. They said, there's nothing that glows that he burnt exactly at that color. We don't know what it is. It's on the sun. And they said, okay, well, look, we don't know what it is. Let's give it a name. In Greek, the name for sun is what? Helios. Let's call it helium. End of story. Over. Except 40 years later, some researchers were burning some gas and looking at the spectrum, and they found that yellow line right at that spot. They were able to say, wow, eureka, that stuff that 40 years ago they observed on the sun, and they knew a physical property of it. They named it helium. We've now found here on the Earth. That's such a great story because it talks about how science works. That we can observe something that's 93 million miles away and then later discover the same stuff here on Earth. So remarkable story. Well, let's move on. If you're into novae, some have deep iron dips. You can see here just with the DSLR, others don't. But quick review here for Doppler shift. Many of you can remember what it is from studies you may have done over the years. The Doppler shift, really briefly, is the pitch change that something makes as it's moving towards or away from you. So when a train goes through a station, it's right, coming towards you, high pitch, moving away, low pitch. Same thing with light. When it's moving away from you, it's as if stretched out, lower pitch or wavelength. And when it's coming towards you, it's smashed together, compressed. Suppose we were expecting to find a spectrum with this triplet. Love that word, triplet, almost self-defining. But instead of finding it there, we observed it down there. What would that tell us? Well, that would tell us there was some Doppler shift in play, that the object was moving away from us because it was red shifted towards the lower, longer wavelength. If it was shifted over this way, we'd know the object is moving towards us. Let's look at a great example, an exploding star. At the end of their life, stars explode in different ways. One way we call type 1A. It's when two stars are circling each other, one dumps gas on another. When you pour gas on a hot surface, what happens? It blows up. Type 1A supernova. Here's one in M101. Now, there's an example. There's a photograph of a supernova remnant. It's not M10, it's not this one in M101, but it's similar. It's a type 1A, and you can see it sort of has an expanding shell of some sort, right? What's it made of? How fast is it moving? Those are the kinds of questions that we ask as scientists. So there's a spectrum, pretty boring. Looks like maybe there's some sort of gap there. So David Strange, with just a 9-inch celestron and less than 15 minutes of integration time, captured that spectrum. And look at that dip. It's pretty pronounced when we graph it, isn't it? So, you know, I hate to resurrect a really overused expression, and that is that we stand on the shoulders of giants. But the giants figured out the different types of supernovae have different spectra, just like elements differ. It's a fingerprint. So, for example, this supernova, right, we said is 2 stars. But what about, there's a different type of supernova where it runs out of fuel, the star does, and it collapses, core collapse. Let's look at really quickly those fingerprints. Here's that type 1A that we're looking at here. Notice that deep dip around 6,000, and that's silicon. Notice that these core collapse types of supernovas, different other types, don't have that dip. One of the ways that amateurs can contribute to the professional community is by helping categorize supernovae. Amateurs regularly do this, not a lot of them, because supernovae typically are pretty far away and dim, so they can be hard to capture. But it's possible. Tim Puckett, who you know, the supernova hunter, a few years ago, he pulled up a screen off of some site that showed just dozens of supernovae that had never been classified. These days, again, telescope assets are, we have a little bit more in the professional world, but it's still a way that amateurs can contribute. Stick with me on this real quickly. David and I measured this wavelength here down at about 6150. So there's how we measured it. If Bunsen had burnt beach sand, which is silicon in the lab, stationary, he would have seen a line at that wavelength. Now, I didn't remember the Doppler shift formula. You know, Wikipedia's your friend. When you plug the numbers in, we have now calculated how fast that supernova shell is expanding towards us by using its blue shift. There should be several wows there. Wow, that's fast, and wow, I can't believe I measured that using a backyard telescope. Pretty amazing. So you may recall Adam Rees and his team, from research they did just before the turn of the century, won the Nobel Prize for studying the cosmological expansion acceleration. And what type of star do you think they used as a standard candle? A type 1A supernova like this. Somehow, I don't think they used this particular piece of equipment, but it's fun to be able to do some of the things that the big boys and girls do, right? So what about the spectrum of a black hole? Well, of course, black holes don't emit light, but the matter in the accretion disk that's spiraling in does get very hot. So David Hayworth captured the spectrum of a quasar, a black hole, and there's the spectrum with 2 little dots of light. Let's blow that up. There are those dots. There's the graph. Now this guy, I don't know whether Brian and Maya made it this far into my talk. If not, of course, no blame. But if you did, this guy was not much older than you. He was in his mid-20s. It may seem like a lot older to you today, but it's not that much older than you. So he wrote about his experience. It's a transcript of an interview, actually. And he said, he looked at this and he's going, what are those peaks? What's all this data? So the first thing he did, like a good scientist, was he started comparing it to other known objects, like the hydrogen bomber lines. These are the lines in my software that show where you would expect, and this is the one I asked you to remember in your mind's eye, expect to see dips. And he went, oh, those don't line up at all, right? There's no dip or peak right where that line is. So we know this, at least these aren't hydrogen features, right? What else could it be? Except they were massively shifted to the red. What that meant is that this object was enormously, as if point to it, 2 billion light years away. And we're able to detect that redshift with a backyard telescope. This is done with a modified security camera. Unlike the images in the backs of the magazines, like sky and telescope or astronomy. You know, you look at those, you go, oh, those are gorgeous. I want to capture some of those. And then you read the fine print. And I do this in my in-person talks. I'll ask for somebody to pull out a magazine, turn to a page, pick a random dark sky object, and then read us the exposure time. And, you know, it's 5, 10, 20 hours. Look, I don't have the equipment, the time, the patience, the knowledge, or the dark skies to do that kind of imaging. I'm glad they do. They're beautiful images. The point of my story is that what I'm showing you tonight is not the cream of the crop. Only the best can do this kind of thing. If you can capture the image of a star that doesn't smear, you can capture a spectrum. It really is that easy. So the Hubble constant tells us this object is 2 billion light years away. Two quick examples. I think it's one of the things that we all enjoy about astronomy is that macrocosmic zoom that we do when we think about how big time and space is. This object would have to be 100 times brighter than all of the stars in the Milky Way galaxy to be that bright as we see it if it's 2 billion light years away. Amazing. And even more fun, I think, if it was only as distant as the star Pollux. I mean, it's a star. I don't have any idea how far away it is, but, you know, stars are really far away. It would be nearly as bright as the sun. Amazing. So the point is that this ancient starlight still has information in it that we can tease out. Subatomic information, right? It's electrons jumping around, and with these coarse wetware eyes and a little piece of glass or plastic, we can extract information. It's as if that light didn't age, right? Other things age a little more quickly. Here's Martin Schmidt when he's 25. Here he is a few years ago. You know, I've been justly accused of throwing the guy under the bus with this picture here, but listen, he's got a full head of hair. I'm jealous of the guy. Give me a break, really? All right, two quick examples and we'll finish up. So far, we've been looking at these kinds of dips. These are hydrogen alpha, beta, gamma. How wide are those? Well, you know, 50 or so angstroms. That's about the best we can do with the grating. If we want to zoom in on one of these and look at the details, wouldn't it be nice if we could just take our mouse roller wheel and roll it? It ain't that easy, unfortunately. It's sort of like when early on in our moon observing career with a telescope, if you're like me, you probably started popping in higher and higher magnification eyepieces because you really want to see more detail of that, that crater rim. But of course, beyond a certain point, it's empty magnification. Same thing with zooming with the mouse or with a bigger grating. To get these details, you need a slit spectrometer to get down to really high resolution. Here's Vega, same feature, and let's compare it to a known object, which is what scientists do. There's the spectrum of the moon, of the reflected sunlight. Notice that feature's in different positions. We're now measuring the radial velocity of that star as it moves towards or away from us. Pretty amazing, but again, that's that expensive device. Last example, I promise. And for that, I am looking for my visual aid, which is here. This is a rotating star. This edge is coming towards you. This edge is moving away from you. So this light is, I can never remember, this light is blue shifted, right? And this light is red shifted. And this light isn't shifted at all by the movement of the star. So if a star is spinning very fast, then we're going to get red and blue shift off those edges, right? Let's take a look at what that looks like. First of all, schematically, this edge is blue shifted, right? Because it's coming towards us. And this edge, the light would be red shifted because it's moving away. There's Vega, doesn't rotate fast, but let's look at Altair. Look how it is broadened and not as sharp because some of the light has been red shifted and some has been blue shifted. So the giants really are smart. They were able to figure out that we could figure out how fast a star was rotating, even at a distance with such simple gear. I think about the giants 3-4 weeks ago when I got my COVID vaccination. I said to the, as it turns out, MD who was giving me the injection, I said, the entire mass of knowledge, this edifice, let's look at it growing, this edifice of knowledge that began hundreds of years ago with a pump handle. If you're not familiar with that analogy, jot it down, pump handle, cholera, and read about the beginnings of epidemiology. Think of the hundreds and thousands of scientists who have gone down dead end paths as well as fruitful paths to end up with that mRNA or whatever was in that injection. It was that little drop took the combined talent and resources of humanity. The giants are amazing and bear us gifts every day. So how do you get started? Well, you need a grating. I've said its name countless times, star analyzer. You need a camera, almost any camera, color, like I said, mono, cooled, video, whatever. You need to be able to track and capture, images of stars. Once you can do that, you screw the grating on. You need software. This is my software. The R stands for real-time spectra, although, as I said, you can use FITS images. This is that shareware I mentioned I tried. I'm friends with the French authors of that. I've hung out with them. Great people, brilliant people. When you say somebody's brilliant, I don't mean to imply I actually am brilliant enough to appreciate theirs. They're really amazing people. But the software still has some problems. It's just not up to the level of usability that we've become accustomed to. And you may need a couple spacers to adjust where the grating is with reference to your sensor, that distance there. So my site has a calculator on it, but oftentimes people just send me their telescope data and I make a quick screen video when they send me the data with this link, and we determine, whether they have green flags, which means they're good to go. So there's tons of books out there. This atlas here is pretty cool. It's linked to on my site. It's that atlas right there. And the cool thing about it is it has tons of examples of what you will see. And listen, I'm not being falsely modest here when I, talk about being a knuckle dragger. That would be bragging, actually, I suppose. But I don't know the significance of nitrogen. But what I do know is that with a reference book like this, which has really great text, and the cool thing is the text is aimed at people like us, not at postdocs or PhD candidates. I can read and learn about what I'm looking for. We've got a great forum online. The software is free for 30 days. The AVSO has jumped into spectroscopy. Stella Kafka, great executive director, and her predecessor, Arnie, both professionals. They understand the value of spectroscopy. About 4 years ago, I gave a live workshop in person in LA. Everybody had laptops and my sample data and my software, and we recorded that workshop. You can download the software tomorrow morning. It's Saturday morning. Download the software from the download link on my site. Download the sample data and then play the video and go through the workshop on your own, even if you never plan to do any spectroscopy. That's a fun activity. When you're done, you actually have it in your bones how this all works. There are opportunities to contribute to the professionals, not as many as we'd like. The AVSO now has a database online for spectra that you can contribute to, like their photometry database. So we've come a long way in the last 200 or 300 years, and forgive me, I've overrun about 55 minutes in, I think. We've come a long way in the last hour. If you stuck with me, I appreciate it. I certainly understand if a lot of this wasn't of interest to you. I hope some of it was and that you came away with a deeper understanding. I didn't get to see you smiling at my jokes. I apologize, or I'm sorry for that. But listen, if you've got questions, I'm here to answer them, whether we do it tonight or whether we do it via these contact methods. I hope you will jump in and take advantage of my being here tonight. I'll be here until John sort of drags me off the stage with one of those hooks. Take it away, John.
Tom, that was absolutely fantastic. I can't thank you enough. Tom, I got to tell you, so I have quite a bit of experience teaching astronomy. I've taught at the college level, and a lot of what you've described tonight, from how spectra work, what we can learn from them. The history of it, the old Harvard calculators, all that kind of stuff is stuff I'm very familiar with and stuff that I've taught myself. But the way you present it, the enthusiasm you bring to this was fantastic. I am ready to run outside and start doing spectra. That was fantastic. I can't thank you enough, Tom.
Thank you. You are a performer if you're a teacher. You've been down that road.
So absolutely. Does anybody have any questions for Tom? Please feel free.
Yes, I have some questions that have come in throughout the presentation. So if people want to type in the chat, you can type in the chat and I will moderate the questions from there. If you do want to just come on and talk to Tom, just send me a note in the chat and I'll work my way through. So I'm going to start with a question from YouTube from Doug Curry. And he's found the presentation very, very interesting. And he'd like to know where he can get a copy of the periodic table that you showed at the very beginning. So where can he get a copy?
And my kind of guy. Thanks for asking. Let's check it out here. So on this site, I need to share my screen, I guess. It's on our site. You can order it. It's $29.95. And if I was a little better at clicking, I'd be able to show you the screen. But somehow I'm unable to at this moment. But I'll put it actually here in the chat window, rspec-astro.com. And while you're taking the next question, I'll try and pop up the screen so that you can actually see where that is on the site.
All right, perfect. Thank you for putting that in the chat. That really makes it easy for everybody to be able to go and find it.
Oh, who's that fellow? So quick story here. This is celebrity worship.
Yes.
I wish I could say I was buddies with him, but I can say that he told me himself that he has this poster hanging in his office right now. And he's as nice a guy as you'd think he is, which means really nice. Just the one story, this was outside a theater here in Seattle. So it's not like I had coffee with him. It's like I grabbed him on the sidewalk. And it was like midnight and, he's walking out to his car. He'd been doing signings, till from like 10:30 to midnight. He said, we're behind a Jersey barrier. He says, I just, no time, gotta go. And I'm holding the poster up and people are saying, Dr. Tyson. So he sort of comes over and he looks up at the poster and he goes, oh, that's brilliant, brilliant. Can I have one? Well, my wife in her genius had sent me with several posters in a tube. So I gave him one or two. So, but then coincidentally, this is a story very brief. Coincidentally, the next day I was going to be doing a solar star party. And it just occurred to me, he was here for 2 nights. It occurred to me, I ought to invite him. So I said, hey, Neil, tomorrow I'm going out to an underprivileged school. I thought that would be helpful. An underprivileged school, kids who are underprivileged, to do some hydrogen alpha telescope work. Would you like to join me? So he stopped. He didn't say no at first. He sort of looked up and he said, my dance card is full tomorrow. And in fact, I looked at the paper 2 days later and he had spent the day with the Seattle Seahawks talking physics. So I believe him. But imagine he'd said yes. The next question from me would have been, do you want me to pick you up in my 20-year-old Subaru station wagon or should you just bring your limo by? Anyway, that's where you can get the poster, Doug. Thanks for asking the question. Go ahead, Sue. What else do we have?
All right. Our next question is from Andrew Brenyo. Andrew, if you want to put your mic on, you can ask Tom your question yourself if you'd like to.
Okay. Hi, Tom. Just a question regarding how long does an image take if you're collecting data for the spectroscopy?
That's a really good question. I appreciate you asking it. I forgot to mention that. So normally when we capture starlight, the photons from the star fall on a handful of pixels on our sensor. But when we spread the same total number of photons out across hundreds of pixels on our camera, we lose 5 or 6 magnitudes. So whatever you can image now, suppose with your current setup, you can image down to mag 12. That means with a grating in place, you'd be able to image down to mag 6. Now, there's tons of stars at mag 6 that are interesting spectroscopically, but that's the relative limitations that you get. It's not as big a limitation as you might think. Now, the reason I answer that way is now I don't have to know how dark your skies are or whether you're stacking or how much aperture you've got. I can just say whatever you can do now, subtract 5 or 6 magnitudes. Great question, though. I'm really glad you asked it.
Thank you.
Sure.
Our next, I don't know if Brian has a question, but Brian Whitman has something he would like to share with you. So Brian, if you want to show your screen, it's all yours.
All right, so I recently got a new camera, so that's
We got-
pretty cool. Fair enough.
Oh, we've got it outside here for you.
Yeah,
It's still here, Brian. That's the cool thing. Good.
yeah. So I recently took this photo 2 nights ago of the Orion Nebula. I don't have any photo editing software, so this is one shot, nice and quick.
Nice.
Nothing
Yeah, it
too
is.
interesting.
It is.
Wow.
Wow.
Yeah.
Very impressive.
Congratulations.
Thank you.
Basically, his first official foray into astrophotography. And since you were
That's
asking
cool.
about the Orion Nebula,
If you look real close, you can see M43 a little bit there.
Mm-hmm.
Wow.
Very small.
Anybody have any comments or feedback for him on that?
Oh, I think it's great.
It is.
Where am I?
I think that's fantastic, Brian. Very nice.
Nice.
Much better than my first image of the Orion Nebula.
Boy.
Well done indeed.
Well done, Brian.
And the
Thank you.
Bob, any other feedback? The Brian,
Yeah.
really cool. Brian, you know, the cool thing is, I think I just stepped on Bob. Go ahead. Anybody want to say something? I guess not. So
Can I be heard?
Video.
This is an image, Brian, that you'll be showing and remember, or at least remembering decades from now. This is that first image. You don't have that many firsts in life that you remember. You don't remember your first steps or words. Your mom does, but this is your first image. So congratulations. That's good. And it shows that you have a lot of understanding of all the nuts and bolts and what plugs into what and all that chaos. So way to go. Thanks for sharing that.
Thanks, Brian.
Yeah.
Tom, our next question is from Doug Curry as well, watching us from YouTube. And he asked, what limits meters per second less or more in stellar Doppler shift could be observed with different aperture of telescopes?
Yeah, good question. So the that gets into the resolution of your spectrometer. It's partly its aperture. The problem is that almost everything that's in the Milky Way doesn't have enough radial velocity to have enough Doppler shift that we can detect it with a grating. That's why the example I used was of extra galactic object like a quasar or a AGN, a galaxy that has a very compact nucleus apparently. So aperture-wise, you really, in order to get a quasar, you saw that example I showed was a 9-inch with 15 minutes of imaging time in a relatively dark sky site. So with a 4 or 6 or 8-inch, an 8 is pretty much a sweet spot for a lot of spectroscopy. You don't need huge aperture. In fact, the bigger you go above that, it doesn't really buy you a lot because of certain optical issues. With a smaller telescope, 8 inches and down, you really won't be able to detect much except quasars and other extragalactic objects. It's a good question. I'm glad you're thinking about that being something you might like to try. By the way, my site has on it a lot of the examples that I just showed to the group. Just so you've seen that, not only will the YouTube video be available when we're done, I always look at this and go, did I leave anything up there? I wish I hadn't, but it looks pretty safe. But what I wanted to show you was this samples page. This page here has a lot of the samples I showed you and a discussion of them. Again, it's something, there's the quasar, for example, where you can see that redshift. So this is something that you may want to take a look at when you get time. Now, the other thing I wanted to mention, I hope it was effective when I talked about the darn learning curve of a new piece of software and how intimidating that is. One of the things with my software is, and it was a brag, I have been writing software since the 60s, but what I wanted to show you was, unlike hundreds and hundreds of pages of user manual to read, my software comes, and this is something I was doing during my former career in software development before I retired to this, is these are tutorial videos. And they're like 3, 4, 5 minute screen walkthroughs with me yelling like this showing you, it's like I'm sitting there with you, just showing you how to do things. And so you can go through this, at your own speed and come back to it when you need it. And so it makes the learning curve a lot easier. I thought that'd be something that would be helpful for you to appreciate. Other questions?
Yeah, can you hear me?
Yes.
Yes, Michael.
Hi, Michael.
Oh, hi. Tom, I don't know whether you remember, you and I were at Las Cruces together a couple of years ago.
Yes.
Yeah, and I guess you were on the virtual one. Was it done back at the beginning of this year from the AAVSO?
Yeah, there was a workshop I did for them in like November or October in spectroscopy. I was happy to do it. It's of course it's a great group of people. The AAVSO, they've got all the equipment. They've got some fundamental science understanding and have actually done some. The challenge I have with the AAVSO, I mean, quite frankly, it's not a secret, is it's been hard to transition the AAVSO into spectroscopy.
Yeah.
And I'm not sure why. It may be that people have their equipment all set up and calibrated because they do such accurate work, such precise work, that it may be they just don't want to mess with their equipment by putting new components on. But it's also, spectroscopy is very different than photometry. I never really was very excited by studying star brightness. I like the flash of colors and so forth. So are you doing spectroscopy today, Michael? Do you have some equipment when you?
Yeah, well, I've got the star analyzer, plus a number of other pieces of equipment, and I've also got your software.
Oh, great.
And I've been doing it. I've been doing Spectra and keeping catalogs and collections and so on. Our biggest problem here right now is the damn weather.
Yeah.
Oh, it's been awful.
Yeah.
Absolutely awful.
Yep.
Get blue skies during the day and it just clouds over at night, fogs in.
Yeah, it's a problem. It seems to be a bigger problem now than it used to be. The reason I just shared my screen, by the way, I wanted to show you something you could do with your equipment. And I mentioned this earlier in my talk, and I had my mouse on it until I went oh, there it is. So I'm going to pull up a video here real briefly. So this is one of our favorite star pairs, Albireo A and B.
Oh, okay.
This is done with a mono camera, but it's a video camera, and I'm going to play that video. And what you're going to see, in fact, let's just play it for a moment. The image is jumping around, our seeing is changing, so is our spectrum. But one thing that we've done, I didn't get into much detail in the software, is the shape of this curve tells us the temperature of the star, right? If there's more light over here in the blue, it's a hotter star. If there's more light over here in the red, it's a cooler star. So this is a really hot star, Albireo B. It's 13,000 degrees Kelvin. So I'm going to play the video and watch how in the video, I move my mouse over and sample the other star. Now look at the shape of the curve. There's much more light over in this cool red area. This is a much cooler star. So the temperature difference we see visually, we can actually see graphically here. This is one way to tell star temperature. The professional way is we use the presence of lines and so forth. But this is literally why I started all this, because I wanted to be able to do this very demo where we captured the spectrum of a star and could tell the temperature of a double star like this. So I thought you'd get a kick out of that. That might be something for you to think about trying to do. It doesn't have to be a video. It could be a mono image that you captured also.
Well, you can do it with your software.
Yes.
You go into the star types and start right on the left-hand side and move over, and you can see the thing rising up and going right over, almost like an avalanche, down like right into the M-class stars. It's quite amazing.
Yeah.
If you really want to see how stars evolve, it's right there. You can almost make it into a little home video.
You're hired, Michael. Let's check it out.
Just pull up your list of star types. So start right over on the right, or sorry, the left-hand side with the A stars or the B stars? I forgot now.
Hot O stars. Yeah, notice how all the heat is over here.
Yeah, and just go right across with it, and it just.
Yeah. In fact, here, I'll animate that. That's why these buttons are here. It's cool that you discovered this.
Yeah.
So as we go through these stars in temperature order, watch how the amount of heat, which starts out over here, will migrate to the right into the blue and green and finally red. Here we go. So now we're in the B stars, the A stars, see it moving to the right, the G stars, the K stars, and finally the M stars. So these M stars have most of their heat over here in the cool red compared, and even infrared and beyond compared to those hotter stars. That's cool. I'm glad you pointed that out. It's a fun way to think about star temperature and to see, as you said, the Planck curve shows us the temperature of the star. Now, for those of you who aren't quite following the science behind this, frankly, I wasn't either 11 years ago. But again, like I mentioned, once you get a couple of these curves and you see they're different, you go, well, what's that all about? And it begins to grow on you. Other questions people may have?
Coming back to me just for a second here.
Oh, sure.
If you have any more of those elements charts, I'd love to have one.
Yeah, they're for sale on our site, Michael.
Okay, I'll get in touch with you. I've got a couple of other questions I want to ask you, but I'll get in touch.
Yeah, please do. There's a chat app on our site.
Okay.
And even when I'm watching TV at night, my watch will ding me when somebody pipes in. And if my wife is interested in pausing it for a moment, we can chat, or anytime during the day. I'm always with my computer.
Wonderful.
Thanks, Michael. I'm glad you're in the system, and it's great to meet you here.
Oh, thank you. Very, very nice to know you. This has been a great adventure.
Wonderful. Anybody else? You'll get your check in the mail, Michael. Thanks again for your questions.
Okay.
Yes, I got a couple more here for you. Dan Copeland popped a YouTube link into he sent it out to everyone.
Yeah.
Dan, do you just want to speak to that link to let everyone know what it is?
Yes, I would be happy to.
Okay.
I love the attention, but I didn't catch your name, but thank you very much. This is me standing out on our deck here in Seattle, 3 stories off the ground. That's Lake Washington. That's the poster that we're talking about.
Yeah.
And it's a fun poster. If you're a digital nerd, most I'd say 80% of the posters that we sell go to physics and chemistry and biology, and then astronomy teachers. It's very memorable. The typical posters people use in the classroom are literally 50 years old, and this one is more modernized. Thanks for that. What else do we have?
All right, I've got 2 more questions here. Both of them are from Doug Curry. We'll start with one first. He says, thank you very much for the answers. And he said, I heard about professional astronomers detecting the Doppler shifts from exoplanets, but I was interested how close or far from those levels amateurs might find.
That's a really well asked and great question. Thank you, Doug. Again, the science here is pretty simple. And that is, we have a star and we have a planet. And as the planet comes around here, it pulls the star towards us a tiny bit. And as the planet gets around behind the star, it pulls the star back a little bit. I'm not sure I said the right object names there.
That's right.
So the star is actually being pulled back and forth a tiny bit. And so we get that Doppler shift. And amateurs have detected Doppler shift. This is one of those hand warmers that we use when we're out. And I apparently kicked it off using it as a prop. It's nice and warm. Amateurs have detected the radial velocity from or Doppler shift of exoplanets. It's hard to do. It requires several $1,000s worth of equipment and a couple of years of observing, but it is doable. And I think in years to come, as the technology matures and more of us are doing it and asking the vendors for less expensive and higher quality equipment in this world, we'll see more and more amateurs doing that kind of thing. It's a good question. I think it's a common question, but I'm glad you asked it because the 2 most common questions I get are that, as well as, can I do science? Can I contribute to scientific pursuits? And I talked about that real briefly earlier. There are opportunities, not as many as we'd like, and not as many as I think we'll see growing over the coming years. What else do we have, Sue? Anything else?
And this will be our last question for tonight. And this is also from Doug Curry. And he asks if you could explain the values for metallicity of stars. He thinks it is related in some way to the abundance of hydrogen and iron.
It is, but I think I'm going to save that for somebody else, either here tonight or for Wikipedia, just because that's not my strength. And it's not really exactly on topic. It's a great question, but that's exactly what it has to do with. Astronomers talk about metallicity differently than the rest of the world. And there's John, hopefully, to jump in and help explain this. But basically, metallicity for astronomers means anything, above the first 3 elements or so. So it's later stage stars. Go ahead, John. Any help? You need your, okay. Oh, he's begging off too. Sorry, I can't explain it. If you ping me on the contact form on our site or by our chat form, we could talk about it a little bit more. Sorry, I don't want to get into much more detail here. I'm liable to mislead people because, like I said, one-trick ponies are good at one trick typically. Anyway, thank you all again. Sue, thank you. John, thanks for setting this up and for all you do in other meetings. For those of you who do outreach, I give you an enormous amount of thanks and appreciation. You know, just to finish up, you know, we all are privileged. Thanks, Bob and Dee. We all are privileged. And the evidence of that privilege is that we're here tonight and that we understand and enjoy these topics. And we've had the opportunity to take advantage of opportunities that we faced and we were given. And by doing outreach, we give back. It's nourishing, and it also, again, giving back, giving forward, giving backwards. So if you're not doing outreach, I'd encourage you to think about doing it. It's fun. I like solar outreach during the day so I can see who I'm talking to. There are solar spectrometers, and I've been looking for a video, which I can't seem to find. There is a solar video spectrometer, there's a solar spectrometer that lets you see these lines on the sun during the day. It's small, it's about this big. It's by a company called Shelyak, S-H-E-L-A-K. If you're interested, ping me and I'll send you the video as I frantically try and find it here, because I know it's here somewhere. I'll send you a link for the video and you can see what it's like. It's really pretty amazing what you can do. And much like spectroscopy, if you're doing solar spectroscopy, much like spectroscopy at night, solar spectroscopy during the day obviously helps augment your current outreach efforts with yet another thing which you can use to discuss with people who are coming to your outreach. You can talk about the solar spectrum and some of the science involved in it. I can't seem to find that video, so if you're interested in it, just let me look in one other spot. Oh yeah, here it is. Okay, I'm going to post here a video link and I'll post it in the chat. Actually, better than that, I'm going to download it right now and I'm going to take another moment of your time. And that way, we're going to watch that video. Give me just a moment. I'd rather show it to you. It's such a terrible video that it's much better to just show you here on the screen. So give me just one moment to download it, and we'll grab it and we'll play that video. And Sue, I hope you'll forgive me for going one moment further. Okay, so let me share my screen and we'll take a look at this. This is a video I made in my front yard to show a friend up in BC. So it's not great. You can see my screen there, I hope. So there's the device, and you don't even need tracking with this device. It's got an eyepiece on it, and you just point it at the sun. You aim it with this little what's called a gnomon. Now, this has a slit on it, which means you're only seeing a tiny piece of the long Roy G. Biv spectrum. So you use this little tuner to look in and see at different places. And you're going to see me tune to look at magnesium, which has 3 lines right next to each other. Let's take a look. It's an embarrassing poor quality. It's my iPhone held up to the eyepiece, but this will give you the general flavor. The colors are gorgeous. There is a magnesium triplet. It's way above my pay grade. It's quantum mechanics as to why there's a triplet instead of a single line for magnesium. And now I'm rotating that lever up to, and the colors are so gorgeous in person. That's a hydrogen alpha line in blue, or I'm not sure which line that was. There's the maker of this device. It's made by Shelyak. There's my shoe, which doesn't have much value here. I'll show you one more line, and that is what's called the sodium doublet. It's 2 lines, and there they are. So this is the kind of thing, just by rotating that little lever, you can look at different regions. People love the colors for good reason. There's the lever moving. The only downside to this is, and I sort of saved the worst for last, it costs about $1,400 US. It's expensive. But again, it might be the kind of thing that the club would buy, or some of you would share in. Like I said, especially when you've got people queued up to look at a telescope during the day at a hydrogen alpha filter telescope, you can set this up next to it. Now you have twice as many telescopes and different topics to talk about. Okay, I'll shut up and wish you all a good night. Thank you again for all that you do, and I'll leave and allow you to now talk behind my back about how it went tonight. Thanks again. John, thank you. We'll talk again, I hope.
Tom, thank
muted, John.
you. I can't
John, you're
say
muted.
enough.
John, you're muted.
I am unmuted. Can
Still
you
can't
hear
hear
me?
you. You're
Oh
no longer
my.
muted. Maybe your mic is turned off.
No, I can hear John just
Outside the
fine.
software.
Tom, can you hear
Anyway,
me?
oh, that was me. My speaker was off, not you. Good night.
Oh, good. Okay. I feel better. It wasn't me. Tom, I can't thank you enough. That was educational. It was engaging. And this is no small thing too. It was entertaining. And I just don't have the words. So what we're going to be able to do is we're going to be able to provide a link to your website, right? You know, these folks can connect to that through our website. And so that they can find it and get to it easily, because obviously, as you can tell from the questions and from the response, obviously you have an enthusiastic group here that you've managed to connect with very well. And so I can't thank you enough.
You're welcome. You have already thanked me enough, and I appreciate it. This, by the way, and I'm not just slinging it here, this is a higher turnout than most clubs get, and I've talked to 350 clubs in the last 7 years, and 150 in the last 13 months. And also the questions are better than the questions I normally get. So congratulations. This is really a very capable group. Good night, everybody. And Brian, send me images. I want to see what you're doing. Good night. Thanks, Doug, for your questions. Nice to see you in video. Bye, everybody.
Thanks, Tom.
Thanks,
Bye,
Tom.
Bob. Thanks.
Nice to meet you.
Nice meeting you too. Bye, guys.
Well, everyone, I enjoyed that immensely. I hope you did too. At this point, we would normally take a little intermission and come back with Matthew Mannering at the Sky this month. Unfortunately, Matthew can't be here with us tonight, and so we're going to have to do without that. Matthew's going to need to take a little time off. His absence will be keenly felt, but he's dealing with a family crisis, and we're certainly going to miss him, as we will miss him tonight. However, I would like to point out here that we have some amazing people who are in the future are going to be filling in for him. You've noted in the past that there have been a couple of times that Bob Christmas has jumped in and written the Sky This Month column for the EH. He's done a wonderful job in the past, and Bob is going to take that over and do that for us. And next month, we're going to have Christopher Stretch giving us the Sky This Month. And I'm very, very much looking forward to that. So since we don't have the Sky This Month to come back to after intermission, I think that we should just go straight into the door prizes. That's always good. Straight into the door prizes. And we can do that right now. Now, I have some door prizes here, and I'm going to show you. Maya, are you with us there?
Yes. Hello.
Fantastic. So Maya, of course, always does a wonderful job. She's been the person that's found great homes for all of these door prizes. She's the gift giver as it is. And that's a bit backwards at the moment, because Maya should be on the receiving end, because tomorrow is Maya's birthday, isn't it, Maya?
Yes, it is.
Yes, it
Turning
is.
14.
So,
Happy birthday.
to Maya.
Thank you.
I'd be delighted if everybody just took a moment to turn their microphones on right now and say happy birthday to Maya.
Happy birthday.
Happy birthday.
Happy birthday,
Happy
Maya.
birthday.
Thank you very much.
Happy birthday.
Wonderful. So tonight we have 3 books that we're going to find good homes for, and a couple of them are appropriate to the evening. All right, here we have a copy of The Glass Universe, and you heard Tom talking about the Harvard computers, people like Cecilia Payne, Annie Jump Cannon, who were the first to to catalog stars by their spectra, come up with the spectral system, and this book is all about that. I can't say enough good things about it. So there we have a copy of that. We also have a copy of this wonderful book here called Light, the Visible Spectrum and Beyond. So this is a lovely, large, hardcover, beautiful picture book with that discusses the full range of the spectrum and all the different ways that that it manifests itself. And for those that are itching to get outside and do some actual backyard observing, we have a copy of The Backyard Astronomer's Guide by Terry Dickinson. All right, just one of the best amateur books you can get there. So we need 3 lucky winners, Maya.
And I have them. So, as per usual, I used our percentile dice. Whoop, I dropped them, but yeah. And our first winner is, assuming I'm pronouncing this correctly, Slanye Medeiros. Sorry. Correct me if I'm
Yes,
wrong.
lunch. Close enough.
Sorry.
Launch, congratulations. Yay. So you're a winner, a door prize for you.
Awesome. Thank you so much. Just a question, how do I collect the prize?
So as always, door prizes, because we're not live in person like we usually are for our meetings, door prizes are available for porch pickup here at my house. You can get in touch with me directly, and you have my email address. I know you do. You can get in touch with me directly, and other door prize winners tonight can get in touch with me, and we'll arrange to get them in your hands.
Okay, awesome. Thank you so much.
So Maya, who's
Okay.
next?
Next is Andrew Brenyo.
Fantastic. Andrew, are you still with us tonight? Is Andrew still here?
It doesn't look like Andrew is still here at this point in time.
Andrew. He popped off too soon. So, all right, we need another name, Maya.
All right, we've got Joan.
Joan's here. Fantastic.
Thank you. I'm in Owen Sound, so we'll have to figure out something.
So, okay, well.
I can't get to your porch.
That's good.
So I'll try to get my email to you through Lorraine, if you can help me with that.
So, okay, so Sue, you can connect me with Joan, perhaps?
I can help facilitate this. Yes, definitely.
Wonderful. Okay.
Thank you very much.
So good. Congratulations, Joan. See, you paid to pop in tonight. Good for you.
Yeah, I really enjoyed it. It was a great talk.
And Maya, we need one more name.
Last is Chris Sheetley.
Chris, you still here, Chris?
I'm still here.
Excellent.
All right.
So wonderful. Congratulations, Chris. So Chris, you get in touch with me direct, okay?
Yep, sounds good.
Good, excellent, good. Thank you so much, birthday girl. you enjoy your special day tomorrow, Maya. So, and
Thank you. I will.
congratulations. Congratulations to all of tonight's winners. Just wonderful. So upcoming, let's see here. What do we have to say here? At our next meeting next month, our April meeting, of course, our special guest speaker will be Mary Beth Lachek, and she is the Director of Outreach for the Canada-France-Hawaii Telescope on Mauna Kea. She's going to give an overview of the observatory and talk about the work going on there. I'm very much looking forward to that. And of course, as I said, we'll also have Chris Stretch with the sky this month. The week coming up on Wednesday the 17th is council meeting. All members are welcome to join in. If you're interested, please get in touch with me and we can make arrangements for you to be there. Council is going to be talking about a couple of things, and you're welcome to have some input in this. Council is going to be talking about the different logos that it has used over the past 27 years of the club's history, and what we want to do and use going forward into the future. I would be very happy to hear any input from any members. Please feel free to get in touch with me directly. You know how to reach me. It's chair@amateurastronomy.org. Emails, of course, are also available in the newsletter and on our website. So please feel free to get in touch if you have any input about the different logos that the club has used. Also happy to hear from any members that are interested in participating in our discussions that are going on right now about light pollution, about public outreach, and happy to hear from anybody who has any suggestions or wants to talk to me about speakers and speaker suggestions, or anybody who wants to talk about contributions to the newsletter. Happy to have you involved in that as well. Please don't hesitate to reach out. Speaking of the newsletter, I feel it is worth mentioning that some of the recent issues have been absolutely stellar, all right? There have been wonderful articles coming from the regular contributors like Joanne Salsi, like Matthew Mannering. Bernie has contributed for the last couple of months with his virtual desk. All have been absolutely wonderful. And over the past few months, we've seen some excellent feature articles come from Bill Tkach, from Ray Badgerow, from Mike Jefferson, all right, who did an article on spectroscopy a couple of months ago. I say well done to all of you. Please keep them coming. I love it all. Just excellent. So a month from now, in April, we'll be talking to the Canada-France-Hawaii Telescope. And until then, you know how to reach us. Is there anything else that I've missed before we sign off tonight? Excellent, wonderful. So thank you all for joining us tonight. It's great to see so many friendly names and faces up on the screen. Thank you all. So please feel free to turn your mics on and say hi.
Good go.
And there we go.
So I just did a quick check. That device from Shellyak is kicking in at about 1,550 euros.
Oh.
Oh, well, that's a bite, isn't it?
Yeah. And then of course you've got to get it here.
Yeah, I don't think I'm just gonna grab one of those for fun. But though I have to admit, just that cell phone image that he showed holding it up to the eyepiece, that was really impressive. It worked great. It worked really well.
I wonder, could you? I guess you could use the grading that he has on another device and just project it onto a screen. You do that's $350 or so to do that route versus doing it with through Shellyak.